Hi everyone, happy Monday. In this video, I just want to take a few minutes to show you two examples I wanted to cover in class today, in addition to the related rates worksheet, which you can find in Canvas. So the first example actually picks up right where we left off in class on Friday with that same falling ladder example that you can see drawn out here the way we had it in class. So we have an 8-foot ladder resting against a wall, and the foot of the ladder starts to slip away, and it's still slipping at 3 feet per second. So the top of the ladder is falling down the edge of the wall here. And in class, we had decided to label this side X because its derivative was given, so we know that that length is important. And then we also, to answer the original question, had this side length labeled as Y. So let's change the question in the same scenario and see how that changes what we do. So the new question is this: at what rate is the angle between the ladder and the ground changing when the top of the ladder is 6 feet high? So we're not taking the rest of the information with the 5 feet from Friday. We're resetting the problem to this, right? So the angle between the ladder and the ground is right here. So we're going to call this angle theta. And if we want to know the rate of change of that angle, that means that we want d theta dt, the rate of change of that angle with respect to time. And we still have this given information here that the ladder is slipping at 3 feet per second. So this is still dx dt, which is positive 3 here. So this information together tells us x and theta are the quantities, and we need to kick off with some type of equation that ties together the x and the theta so that we can differentiate it and have these derivatives get involved. So the quantities here, instead of x and y, are the x and theta. I actually didn't need to label that side y, although it doesn't hurt. Right, so if we stare at this picture and think about it, we'll see that the Pythagorean theorem, x squared plus y squared equals 8 squared, doesn't help us here, even though that's kind of our initial instinct when a right triangle shows up. And it's not going to help us because we know we need the angle theta in the equation. So what will work is if we do a SOHCAHTOA proportion instead. So if I have this triangle, this is the right angle, this is theta, this is x, and I know that the hypotenuse is 8. This is the adjacent side over here, and this is the hypotenuse. So to get all of these in one expression, I could do the ka of SOHCAHTOA because I have the a and the h that would come out there. So the adjacent side is what we're calling x, and the hypotenuse we know is 8. So this is kind of out of desperation, but it does work. We know that theta and x are both changing with time, so nothing gets plugged in. We're just going to go ahead and differentiate with respect to t. So the theta and the x get the implicit treatment. Cosine theta, its derivative would be negative sine theta, so we'll throw in the d theta dt. X over 8 is really 1/8 times x. So its derivative would be its slope, which is 1/8. So I'll say 1/8 dx dt. And I'm almost there. We do have that extra wrinkle where sine of theta is not directly provided. So we're going to have to go back and figure it out. All right. So I know that dx dt is 3. D theta dt is what I want. And then we have a little bit of a side project for sine of theta. And if we go back to the original question, you'll notice we haven't used one piece of information when the top of the ladder is 6 feet high. So they're saying when this side, just for a split second moment, is 6, that's kind of our momentary situation. So this is the opposite side that we can fill in only after we've differentiated because it's not a constant value. All right, so sine of theta would need SO of SOHCAHTOA. So in this triangle, that would be the 6 over the 8, which we can simplify to 3/4. That's what I'm going to plug into that spot. Certainly, I could have used the 6 and the 8 to solve for the value of this adjacent side here, but I actually didn't need it for this purpose, so I'm not going to bother. All right, let's finish the problem. So now we have negative 3/4 d theta dt equals 1/8 times 3. I'll multiply over negative 4/3 to cancel out the negative 3/4. So I have the 3 over 8 that was here, times the negative 4 over 3 to cancel this out. The 3's cancel, and I get negative 1/2. It does make sense that this is negative because as the ladder falls, this angle is decreasing over time. And the very last thing I'll do is put units on it. That'll be theta units per time unit, which is actually radians per, and if we come back up here, we have seconds mentioned just once, so I'll say radians per second. I know it's radians and not degrees, not because it was specifically mentioned, but because I differentiated in this moment, and remember, oh wait, this moment right here. And remember we said those trig derivative rules are only true for radians. So right here, I decided that my answer would be in radians. So this is my final answer. Okay, the second thing that I wanted to mention in class was just a slightly more annoying kind of situation in the example. This is my second and final example in the video. We have a conical tank shown below. And I'll mention everything you're seeing on the page right now is a given part of the question. All right, so we have a conical tank with its pointy side down. It has a top radius of 2 meters and a vertical height of 4 meters. It's filling with water at a rate of 2 cubic meters per minute. We're asked to find the rate at which the water level is rising when the water is 3 meters deep. And they're telling us the volume of a cone has this formula because that's not something that most people just know. This is definitely a formula that would be provided with the problem if it came up on a test or quiz. All right, this problem has a lot going on, and it's going to call for a little bit of math that we haven't had to remember probably in quite some time. Okay, so if we're filling with water at a rate of 2 cubic meters per minute, that's the derivative of the volume of water. So that tells me that the volume of water is one of my quantities. Okay, and then we want to find the rate at which the water level is rising. So we want the derivative of the height of the water. So that's not the height of the whole tank. That would be this height here. We'll say big H for the whole tank and then little h for just the water. So what we want is dH dt, and they gave us that dV dt is 2. So that tells me that the height of the water is the other quantity because its derivative is involved. So I need an equation that relates the volume and the height of the water part. And the water itself creates a cone shape because it's inside of this larger cone. So I'm going to use the given volume equation here. Pi over 3 r squared h. And I'm using little r and little h because these are both the dimensions of the water part, not the red stuff, that's the whole cone. So little r is the radius of just that top circle of like the face of the water on top. So little r, little h is the water, big R, big H is the tank. Okay, now everything is changing. The volume, the radius, and the vertical height of this water cone is all changing. So there's nothing to be plugged in for right away. So we can differentiate this as is, but then we run into a fairly problematic roadblock. So if we differentiate from here with respect to t, that's kind of our normal thing. We would have dv dt on the left, pi over 3 carries down. And then for r squared and h, these are both separate functions. So I'm going to do the product rule here. with this F and this G, F prime G plus G prime F, where the R and the H are both getting the implicit treatment. So F prime G plus G prime H, like that. Okay, so we can fill in for some of these things, right? They're telling us the rate of change of volume. We know that this is 2. And we know that the water is going to be 3 meters deep, so little h should be 3. But the really big problems here are this, and especially the dr dt business. We're going to have a really hard time from the given information figuring out what those are, especially, again, the dr dt part. So what we're going to do to make our lives easier is come back here, and before we do the differentiation step, we can actually fully delete the radius from the equation, because the radius and height of this water cone are very, very closely connected in this scenario. So this isn't something that we've had to do so far, which is why I wanted to make sure I pointed this out and talked about it, even though we didn't have class today. Okay, so I'm going to draw this tank again. So this is just the side view of the tank, so it's like perfectly lined up on top, just so it's a 2D image. And then I'm going to have the water level be kind of cut through it like that. So we know that the upper radius here is 2. And we know that this vertical height here was 4, just like in the image above it. And then I also know little r and little h. So what I'm going to do here, really it's out of desperation, right? So I need to know stuff about little r and little h to get this usable. But what I have is mostly information about the tank itself, big R and big H. So I want to connect all these things. And what I'm going to use to do it is similar triangles. These come up once in a while in related rates problems. So it's something I wanted to kind of refresh your memory on, because it's probably been quite a long time. This does come up on the worksheet once in the problem with the shadow. So the two similar triangles that we are looking at are this right half bigger triangle. So its foot is big R, and then it has vertical height big H. And then the smaller triangle within it, that is just the water part right there. So they're similar triangles because they're sharing a kind of a tip down here. They have the same angle right there, and they both have a right angle at the top. So they're pretty much the same proportions, they're just different sizes. So we can use that similar proportion business to get where we need to go, and there's lots of options. So we could say little r to big R is the same proportion as little h to big H, or we could say little r to little h is the same as big R to big H. We can kind of match this up a few different ways. I think I'm going to use the first one, but you can still get away with it if you match it up a different way. Okay, so little r to big R. I don't know little r, but I know the big R is 2. And then we have little h to big H, which is 4. So I'm just going to times 2 on both sides. And I get that at all times, little r is a half little h. So I can come back up here and plug that in for r. So v is pi over 3, and instead of r, I'll write a half h squared h. Simplify this down a little bit. This 1/2 squared is a quarter. Combined with the 3, we get a 12. So I really, oops, I did 2 things at once there. So this would be h squared, and then combined with this h makes an h cubed. We'll ignore this extra h here. I was going to do it in 2 steps and say h squared, h is h cubed, but we'll just keep that cube. So from here, we can do the problem in the way that we're more familiar with. So now we can differentiate with respect to t. and then plug in the stuff that we need. So let's come back to the top. We said dv dt is 2. So I got a 2 right there. We want dh dt. And then the last thing I need here is the height of the water, the little h. And we're saying when the water is 3 meters deep. So then finally that 3 comes in right there, and I can solve for what I want. All right, so here I have 3 times 3 times 3. 3 times 9 is 27. So I have, let's say 2 over 27 is pi over 12 dh dt. And we'll do times 12 over pi to cancel that out. And why don't we call this 24 over 27 pi? Without a calculator, that's the best I'm going to do. I suppose I could simplify that, but I'm not going to bother. dh dt, and I need height units, which will be meters, per time unit, which is minutes. So I'm going to say meters per minute as my final answer.